For many decades, we in the clinical sciences have been assessing our research based on testing and accepting or rejecting a null hypothesis. And we've been basing the acceptance or rejection of a null hypothesis based on the p-value of less than 0.05. And we've been doing this way for decades. However, when we talk about clinical research, we're not necessarily talking about was there or was there not a difference, right? So that the null hypothesis essentially boils down the research question to a yes or no binary response. But in clinical science, we're actually more interested in how much was the effect. It would be very difficult for us to come up with some kind of intervention that we have some logical reason for believing will work, to come up with absolutely nothing. There was no difference between groups. So that we're not really testing was there a difference or was there not a difference. What we really want to test, the more appropriate question for us to test, is how much was the difference. The difference may be small or trivial in size. It may be inconsistent, but certainly there's something going on. So we need to really refine our thought process, not so much to accepting or rejecting binary yes or no, there was or was not a difference, and turn it more into how much was the difference, how consistent is the difference, how likely is the difference to have a meaningful impact on our clinical practice, whether that's physio, whether that's medicine, whether it's sports science, whatever we do, we're looking for clinical results here. So we test this null hypothesis based on the p-value. So anytime that we're doing any sort of statistic, whether it's a t-test, an ANOVA, chi-square, whatever it is, these are all inferential statistics that we're trying to make an inference from the sample that we have to the much larger population. The p-value between two means represents the probability that our intervention effect was not zero. So that's really where the interpretation of the no difference comes from when we're testing the null hypothesis, is that it's testing it's testing the likelihood or the probability that the difference between the two groups was not zero. So p-value, p of less than 0.05, is indicating that the probability that the difference between the two groups being zero was less than 5%. Alright, so this is where our p-value of less than 0.005 is coming from. So the probability that we have some effect that was not likely to be zero is greater than 95%. And 95% sort of seems like a pretty good landmark, I guess. But really, what use is going to a coach and saying that the difference was not zero? So you've done 6 weeks of squat training on a group of athletes, and we want to know how it influences running speed. So the coach comes to us and says, hey doc, how'd all that squatting go? And we reply, well, probably wasn't zero. What's a coach going to say? Thanks doc, see you next year. It's just not a useful conclusion. They want to know what the likelihood is if it actually helped, and how likely is it to help. If we just try to base this on this 0.005 landmark, then especially, but I mean, even if we say it's p is 0.1 or 0.2 or whatever, basing it on some kind of arbitrary landmark, only indicates that the probability that it was not zero. And especially using 0.05, 5% probability that our intervention was not zero doesn't mean that there was no effect. Right? And I found this great quote that surely God loves 0.06 nearly as much as 0.05. So if you were to go to a coach and say to the coach, hey coach, this will work 94% of the time, any coach is going to take that. But based on tradition of null hypothesis significance testing, we would have to accept that null hypothesis and say that there was no difference between groups, which seems pretty ridiculous to me. So I'm particularly find problematic having a p-value as some kind of threshold. And again, it's even if we just took a vague threshold, we're still trying to accept or reject a null hypothesis, did or did not work, which simply is not an appropriate question. 5% is only an arbitrary line in the sand that has no scientific, physiologic, mathematical, or any other rationale for being. So if we, so that the 5% came from, and why do we all follow it if there's no rationale for its existence? That's a really good question, actually. I mean, if you, so if we were to take a cage of monkeys, and so we've got 10 monkeys in there, and we put a bunch of bananas in the cage, and of course the monkeys are going to try to eat the bananas. So as soon as any of the monkeys go for the bananas, we spray all of the monkeys with cold water. They'll eventually learn not to go for the bananas, because if they do, they're going to get sprayed with cold water. So if we take one of those monkeys out, put in a fresh monkey, of course the fresh monkey doesn't know, so he's going to try to go for the bananas. The other monkeys try to restrain him because they know, hey, if you go for the bananas, we're going to get sprayed with cold water. So they actively, this is a real psychological experiment, they actually try to restrain the monkey, the fresh monkey. So we take out another one of the old monkeys and put in a new one. Same thing happens. Take out another one of the old monkeys and put in a new one. So all the while they're restraining, but none of them are getting to the bananas, so that none of them are getting sprayed with cold water. Eventually we've replaced all of the original monkeys that were trained with being sprayed by cold water. We put in a new monkey. It tries to go for the bananas. All of the monkeys try to restrain the new monkey, but there's no original monkeys left. So they're restraining this monkey from going for the bananas. They have no idea why, but they do it because that's how they were taught by their group. The same thing is going on here with 0.05 and null hypothesis significance testing. Nobody has any concept of why or where it came from, what it means. They simply accept or reject their null hypothesis because that's the way it's being done, and that's the way they learn to do it. But there's no sense in it. So it's time for us to change how we think about our research, or the interpretation of our research findings. The idea of assessing based on normal distributions comes from this, well, it's a paper by just a guy named Student. And his real name was William Seeley Gossett. And he was a brewer. And what he wanted to know was, he got tired of dealing with moldy bags of grain. So he wanted to know if he could predict what the bag of grain was like simply by pulling out a handful of the grain, and so taking a small sample, looking at the amount of moldy grain within that handful, the number of grains that were actually going off, and seeing if he could make a prediction about what the rest of the bag was doing based on just that handful of grain. So he developed the t-test, also known as Student's t-test. And of course he was unfortunately a brewer, so he never would have been able to publish this in proper scientific or mathematical journal as a brewer. So he had to publish under the name student, as a nom de plume, so to speak. This is a photo of William Seeley Gossett, which I love just because of the sideburns. That's great sideburns. So, so this is where the student t-test comes from, and you can see that up here we've got 1923, so that at no point was he trying to accept or reject a null hypothesis. All he was doing was trying to make inferences from the sample to the much larger population, or the sample of grain in his hand to the population, which is the entire bag of grain. So we then ended up not too much longer afterwards, with a fellow named R.A. Fisher. And in 1925, Statistical Methods for Research Workers, he used this normal distribution and two standard errors away from the mean, or the zero, I suppose, which is our landmark, the no difference, and said, look, if we're more than two standard errors away from the zero, then we've got a pretty high probability, or 95% probability, that the mean is well away from that zero. It's far enough away from the zero that we can say with all confidence that we should probably accept what's going on. He referred to it as a convenient convention. It's just twice the standard error, right? So it was more out of convenience than any mathematical or physiological or scientific or medical reason for being. It was a convenient convention. He then coined the term null hypothesis in 1935 in a paper called The Design of Experiments. So up until 1935, it was simply saying, look, two standard errors was, probably something realistic going on, something worth taking note of. And then he said anything less than two standard errors we should probably reject. Okay, so he's finally come to this accept or reject differences between a sample and a population. So this kind of ticked along, this idea, for quite a few years, a few decades actually, before it really got accepted. So, and the idea really didn't take hold. And if you ever question the value of coming up with a great title for a paper, so he came along with this work in 1935, but it wasn't long, or it was a long time later, and then bam, he comes up with Mathematics of a Lady Tasting Tea. And this comes 1956, and this is where the null hypothesis significance testing really took off. And so in this paper he describes, he's got an aunt, and this is a real story, and he wrote a paper about it, that she claimed that she was able to taste the difference between a cup of tea that was made in the pot made in the cup, if you left the tea bag in and added the milk, versus if you took the tea bag out and then added the milk. And she claimed that she could taste the difference. So in this paper, he describes what an experiment would look like to either prove or disprove whether she could or could not taste, whether they arrive at the conclusion by the end of the experiment, whether she could or could not taste the difference, whether she was right or wrong. And that's where this right or wrong, yes or no, accept or reject really took a hold. And well, unfortunately, we've been sort of stuck with it ever since. So this accept or reject simply describes the testing of the null hypothesis and statistical significance. But it's uncommon for a researcher to talk about their rejection or accepting a null hypothesis based on its statistical significance, right? There was no statistically significant difference between groups. They'll usually simply abbreviate that to there was no difference between groups. And that's a big difference when you consider the interpretation that we're not confident in the difference, right? And that's saying there's statistical significance, 95% likely, or 5% probability of being zero, right? We're not confident in that result, and therefore we are just going to simply reject or accept the null hypothesis, as opposed to the confident conclusion that there was no difference between groups. And that's the modern interpretation. So when we describe it, the statistically significant result or lack thereof with the mean, we generally accept, or most researchers interpret that as this is the precision of the mean, so that we have a 6% improvement in performance, p of less than 0.005. Therefore, that p, that mean, is pretty accurate. That most participants fell somewhere around 6%, or they were 6% improvement. And we're using the alpha, the 0.005, to determine if there was or was not a mean effect. Actual, like I said before, is probability of not zero, so that we've got the difference there in the interpretation is that we have p of, or an improvement of 6%, p of less than 0.005, and we think that that's pretty much where the result we can expect is, around 6%. But in fact, the actual interpretation of that is simply not zero. It's not the precision of the mean per se, it's simply the probability that the confidence goes below 95%. The other problem with so that there's certainly an interpretation issue when we talk about the null hypothesis significance test and the p of less than 0.005. That people believe that it is it's the precision of that mean, how accurate is that mean, and they expect that if there is a p of less than 0.005, they can expect the mean. And then just the whole premise of the accept or reject there was or was not a difference, there was no difference between groups, is also simply not accurate. So there's problems on accepting a null hypothesis, and there's also problems with rejecting the null hypothesis. The other problem with the null hypothesis significance test and the p-value of less than 0.005 is that it does not capture the concept of magnitude or the meaningfulness of a change. So p-value does not give you any idea of the impact that the effect can have on performance. Is 10% increase in bench press strength 6 weeks good? Well, I mean, it sort of depends who you're talking about. That if these were elite powerlifters, 10% improvement is massive. But if you're talking about, untrained people, then 10% is pretty miserable. So we need to have some sort of consideration about who we're talking about here. If we've got, so we pull on the Kathy Freeman speed suit with the Lycra hood and we put that on, and we can find a statistically significant improvement of 0.006 seconds over a 100-meter sprint. Is that good? Well, I mean, in an Olympic final, probably yes. But on a group of school kids, probably not. Okay, so not all statistically significant results are large enough to impact, for example, on the placing of a race. So that if we look at two different races, right, so we've got the kid up front here, looks like about to win, and then we've got the kid back here, looking like coming pretty much last. So Is 0.06 seconds going to take her chances and improve them into a medal contention? No. Whereas if we look at what's going on here, 0.006 could actually have a pretty meaningful impact on performance. So really what the question is how big a change do we need to actually make a, I don't know, we're still struggling with sort of the phrase we want: practical difference, meaningful difference, substantial difference, worthwhile difference, anything but a statistically significant difference. So we're trying to stay away from that phrasing of statistically significant. So in order for us to come up with the answer to how big of a change we need, so the lack of a magnitude and the lack of magnitude and concluding that the result was not zero, both of those lack usefulness. We're looking for useful implications of our research. Doing so with a mean and a p-value simply does not accomplish that. You can't go to a coach and say, probably not zero. It's just not a useful finding. So we need to find some way to quantify the meaningfulness. And this is not just something that I'm making up. This is not something that a new concept that Will Hopkins, who's sort of pioneering this type of data expression in sports sciences. Other areas have been doing this for a long time, have known that p of less than 0.005 in a clinical science is not useful. So we've got papers like the so what factor, and we're really trying to get to statistical versus clinical significance, why permutation tests are superior to T and F tests in biomedical research, significance test harm progress in forecasting, and we're not talking weather forecasting. So that if we look at International Journal of Forecasting, it's not weather forecasting. It's just making inferences about future events. So significance tests harm progress in forecasting, and then certainly one of the greatest paper titles, again back to the, actually no, not yet. This is another good one. Why most published research findings are false. And then another one where you don't want to doubt the impact of a great title, The Cult of Statistical Significance. I love that one. Okay, so again, this is not a really new area, or a new method of data expression, trying to find meaningful inferences, not just statistically significant inferences, not just not zero, but really interpreting your data. So we go to and let's have a look at an example. So you're currently preparing athletes for the 2012 New South Wales Country School Athletics Championship. As a sports scientist, I demonstrate that 6 weeks of heavy squat training can improve 100-meter sprint time by an average of 0.04 seconds. As a coach, is it worth you including this training in your athlete's program? What if the improvement was 0.14 seconds? What if the athletes are Olympians going to London? Okay, so there's a few different questions that we need to ask before we determine the impact that this research will have. Statistical significance or not, be damned, doesn't matter. Okay, we've got 0.04 seconds, 0.14 seconds, school kids versus Olympians. But there's a few things that we need to consider here. First thing that we need to consider is level of performance. So if we look at what normal distributions look like, this red normal distribution here in the middle might look something, our blue kids, right, because they finish with quite a wide distribution. The whole point of the shape of the distribution is it's telling us how far apart our scores are from the mean. That's what a standard deviation is it's assessing how far the normal score is from the mean. Whereas if we take our red distribution, right, these are almost all finishing at the same time, right? So we have a very tight standard deviation. So the magnitude of performance necessary, or of improvement necessary, for this group is much smaller. They only need a very small fraction in order to improve their chances of finishing one placing or two or three placings ahead of their competition. Whereas here, the magnitude would need to be much larger. Okay, so that what's important here is the standard deviation of finish times. Okay, and we're going to base our calculations of the necessary magnitude based on standard deviations. So what we're going to do is we're going to go back to 2011 finish times and take, there's the finish times, and what we're going to do is we're just going to simply calculate a mean and a standard deviation. Now, how do we use that information to calculate how big of a change we need in order to say, hey, this is important, this is really a relevant intervention for you to take. So once we know how much the normal variance between athletes is, we can determine how much improvement is necessary to substantially increase the athlete's chance, which is to say the likelihood of moving up in the placing, right? Because it's all about, if we go back again, it's all about how big of a change do we need in order to place above somebody else. That's really all that we're talking about when we talk about athletic competition, is placing more than higher, faster, whatever, than somebody else. So according to Jacob Cohen, so 1988, developed the Cohen's D. And what we're going to do is take 0.2, which he determined was a small effect, which we'll refer to then, this calculation, as the smallest worthwhile change. So if we take the standard deviation times 0.2 equals 0.075, 0.075 seconds is the smallest worthwhile change that we need in order to say, hey, that's a relevant finding. That's big enough for us to really consider. There's the group standard deviation. 0.2 is the constant. So if an intervention can take 0.075 seconds off my athlete's time, it's probably not. So if it can't take that much time off my athlete's time, it's probably not going to help him place any higher. Note the smallest worthwhile change varies depending on who you're talking about, because the standard deviation is going to change. If we have our Olympians, we have a very small standard deviation, and therefore when we multiply it by that 0.2, the result doesn't come out as very large. Whereas if we take our school kids, then the standard deviation comes out much larger, and therefore the smallest worthwhile change comes out as much larger. The other way we can interpret this Cohen effect size is by calculating the difference in the means, so that we've got a post-intervention mean. So we've done 6 weeks of squat training. We're going to take their 100-meter sprint time and subtract that from their pre-sprint time and divide it by the standard deviation. It will usually come out as some kind of coefficient. If it comes out below 0.2, we call that trivial. It's just too small to worry about. Right? The mean didn't have enough of an effect on the standard deviation to influence finish times or finish placing. Put me faster than somebody else. 0.2 to 0.49 we'll call small. 0.5 to 0.79 is moderate, and anything larger than 0.8 is considered large. Important to note, do not confuse the Cohen's D effect size with what SPSS calls an effect size in the options of the ANOVA. That would be a partial eta square, not a Cohen's D. Even though they both come out as similar looking coefficients, don't confuse the two. SPSS will not do a Cohen effect size. You need to hand calculate that in an Excel. So where I test the consistency of an effect with an inferential statistic, I test the magnitude with an effect size. So if we've got that 0.04 seconds divided by the 37, that's going to tell us that the effect size is pretty much trivial. If it was 0.14 seconds, so we've got the same distribution here, the same group, the same population, or same sample, sorry, the effect size, and all we've done is made our intervention much larger. Well, all right, well now we consider that small. If we have that same 0.04 seconds, but have a much tighter standard deviation, we're going to come out with a moderate effect, right? So that the size of the intervention and the standard deviation of the group that we're talking about gives us the effect size. So effect size puts a variety of different measures into a constant scale for ease of interpretation. So what I'm doing here is I have my effect sizes, and I had a mean change. I'm trying to remember what, something about EMG, I think. So we're talking about head placing, and we're comparing 8 sets. No, this was warm-up activities, and this was a star excursion balance test. And so if they did 12 sets of this dynamic warm-up, we can see that improvement in the star excursion balance test improved by sort of 0.4243 of an effect size, which is small. Anything in this gray area gives me a trivial effect, right? So we can say 4 sets of static warm-up or 8 sets of static warm-up had a trivial effect on star excursion balance test. The larger volume had a small effect, and in fact all of the remaining ones come out as small. Okay, so I found this is actually a pretty useful way for interpreting a large number of variables for the impact that they can have. Anything outside of this gray area is going to give me at least a small effect. I've also landmarked moderate and large as well. Now the problem with this is that it is only using mean, and of course this is giving us impact, but it still isn't giving us any sort of measure of precision. Okay, so it might be that we had one extreme score or 2 or 3 extreme scores that did really, really well, and everybody else did terribly on the test. Okay, but those extreme scores are pulling my mean up, so that we know that a mean is not enough. So that we need some kind of measure of precision of that mean as well. Now the 95% confidence limit allows us to give us, so that we come up with this mean, and that gives us some kind of point estimate. Okay, so that if I take the average of 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20, my mean is 11. Okay, so that the mean represents a point. It's a point estimate, but it's not necessarily a score that actually happened. Okay, so it's a mathematical calculation, it's a point estimate. So real people are not mathematical, so there's obviously some error in that estimate that math can't account for, right? So we've got the mean of 11, even though all of the numbers were even. There's bound to be some error. To estimate what a mathematical formula cannot account for, of course, a second mathematical formula has been developed. I just love statisticians. So what we're trying to do is figure out how to quantify variability. Okay, so that we have a 6% improvement in 100-meter sprint time. Does that mean that every single participant will have a 6% improvement? Well, no. Some had 4% improvement, some had 3% improvement, some had 8% improvement, right? So there's a certain amount of variability in that 6%, so that when we go to a coach and say there was a 6% improvement, p of less than 0.005, the coach is expecting 6%, but that's not really right. That maybe nobody got 6%. So what we're trying to do is we need some kind of measure of consistency of that 6%, right? So that did some participants come out as 6%, some were 6.1, some were 5.8, some were 6.4, or was the mean 6%, some were 30%, some were minus 10%, some were 20%, some were minus 18%, right? So the results are just all over the place. So, or are they very consistent? So that we do still need students' t-test in order to figure out what the likelihood is, or the probability is, or to quantify that variation. So what we're going to do is we're going to use a student's t-test. The 95% confidence limits indicate the range in which the real score probably lies, right? So that we've got a mean estimate, and then we're going to put a 95% confidence limit on that in order to sort out where the likely range is. So that we've got a mean estimate of 6%, but it could be anywhere between 4 and 8%. Okay, so that when we say to a coach, when the coach says, hey, how much improvement can we expect from my guys? You can say, well, we expect it somewhere between 4 and 8%. And the coach goes, oh, all right. Right, that's useful. That's a useful finding. It's not an effect size yet. We'll look at how to convert it into an effect size in a second. But to give a mean and then a confidence range is so much more useful. It's still using the same test. It's still using the student's t-test. But we're quantifying the variability in the response rather than simply giving a mean and a conclusion about 0 or not 0. Right? It's useful versus not useful findings. So confidence limits are derived from the mean and the p-value, which is derived from the student's t-test. The mean lies in the middle of the lower and upper confidence limits. So that if we have a 5-second improvement, so we've gone 5 seconds faster, 95% confidence limit, somewhere between minus 1.22 and to 0.19, and actually might have actually increased running time as opposed to decrease it, right? But at least, we're accounting for that. We're just saying here's the range. Here's what you can expect from this intervention. Okay, so we've got the same table of expression of results here, but now I've added not just the mean, but I have confidence limits on this as well, right? So that we can see that our 12 sets of dynamic, the effect on star excursion balance test is almost, there's a slight part of the 95% confidence limit that's extending down into the region of triviality. I'm calling this the region of triviality, a term coming from Will Hawkins. But certainly most of it, we can say that there is a very good likelihood that we can improve star excursion balance test with 12 sets of dynamic warm-up. Whereas 4 sets of static, you can see pretty much the entire thing sits in the region of triviality. 4 sets, it's still mostly region of triviality, right? So that we can conclude that these results, that the 4 sets and 8 sets of static warm-up, probably has a pretty trivial effect. Right? We're not saying no effect. We're saying that the effect is probably is likely trivial. Whereas here, 8 sets or 8 to 12 sets of dynamic warm-up, the likelihood that improves star excursion balance test by a meaningful amount, not just a 0 amount, but by actually a meaningful amount, is quite high. Now, lots of people will come back to me and say, well, look, it's sounding all pretty subjective, like you're interpreting 0.2 as meaningful. Well, that's as subjective as 0.05, isn't it, right? It's a meaningless, arbitrary line in the sand. Does that make it scientific that we're applying, where are they now, these qualitative descriptors? We're actually interpreting small, right? It's not numeric, it's a word, it's small, it's a qualitative descriptor of what's going on, right? And again, lots of people will tell me, oh, look, it's being pretty subjective, it's unscientific. What exactly is all of the basis for this? Yeah, okay, maybe. But I think that trying to interpret results only on what the numbers tell you is pretty silly as well. So we look here and we say, look, here's our confidence limits. Right? It goes from here to here. Now, what a coach decides to do with that kind of varies. What they're going to do with this intervention might vary. Okay, this one's down here is pretty clear. What about this one? All right, there's still a pretty substantial amount of confidence limit that's going down into the region of triviality. Okay, so that if this was impact on 100-meter sprint time, a coach might say to me, hey, what's the likelihood here? That should I do this or not? And we'll go to the coach and we'll say, look, you can expect the impact to be from this much to this much. Now, if I am coaching somebody who's probably going to get, fourth place, right? He's looking at the competition. He says, look, I'm not going to beat that guy. I'm not going to beat that guy. I'm not going to beat that guy. All right, I'm probably looking at fourth place here. So let's take this intervention here. You can actually see that a lot of this is in trivial. There's a slight margin, not a slight, maybe a substantial margin, that's in possibly helpful. Some of this is actually possibly harmful. Okay, so I've got the guy in fourth place. I'm coaching, he's my guy, he's who I'm coaching. And so look, here's the effect size, here's the confidence limits. It might actually be detrimental to his performance. The coach might say, well, fourth place, fifth place, sixth place, screw it, who cares? I'm out of medal contention. But this might actually push me from fourth place into third place. It's a small likelihood, but it might. All right, let's give it a go. Same result, different guy. This is the guy that's likely to win. Maybe second place, but probably first. What's the coach going to do? Look, there's actually a substantial chance that it's going to knock me from gold to silver, or silver to bronze. Ugh, no, get me out of that. I'm not going to do it. The point is that it's leaving the coach, who's the clinician, right? Whether we're talking medical doctors, coaches, strength conditioning coaches, physiotherapists, it's leaving the decision in the hands of the clinician, not in the researcher. As a researcher, I'm simply expressing my results. I'm saying, here's what you can expect. What do you want to do with it? That's up to you. But here's what you can expect. It is not my job as a researcher to say, use this, don't use that. Okay, I want to leave that decision in the hands of the clinician. Okay, so like I said, this is sometimes criticized as being subjective or scientific because all I'm doing is I'm providing you with results and I'm allowing clinicians to make the decisions. Is it subjective? Is it scientific? Well, saying yes or no based only on what our numbers are telling us, published in Nature, momentous sprint at the 21:56 Olympics. Women sprinters are closing the gap on men and may one day overtake them. Right? So that what these researchers did was that they simply ran pretty much a linear model and said, look, women are increasing at this rate, men are getting faster at this rate. Women are actually improving faster than men, and if you run that as a linear regression, run both of those as linear regressions, eventually men or women overtake the men because they're improving faster. published in Nature. Simply because, so they removed logic from their decision-making process. And they just said, well, here's what our numbers say. So that's what the numbers say. Women will run faster than men one day. Right? So that Tim Noakes, I saw him present a further extrapolation of this and continued to draw the lines further and further out, and demonstrated that, I think it was by 25 something one year, that women will then not only be running faster than men, but will also be running faster than combat jets. So just, completely removing logic and thought from research simply because that's what the numbers say. I think that's another ridiculous way to interpret p-values and means, and if it needs to be interpreted, not just numerically expressed. So at no point do I say yes or no. I'm simply giving probabilities that the treatment will have a substantial or meaningful but not significant effect. I'm allowing for room for logic of a real person to interpret results. The result has to make sense in order to be meaningful. We don't just accept or reject a result based on its statistical significance. It needs to have a substantial impact, which we quantify with a Cohen effect size, and there needs to be some kind of range of interpretation, which we express as a 95% confidence limit. So our mean is that measure of central tendency. Our standard deviation is a measure of distribution. D is the measure of magnitude. Confidence limit is the measure of precision. P only gives us not zero. Right? So if we could drop any one of those statistics, we want to know sort of what sort of result can we expect, what's the range of results that we can expect, how do they distribute, how big or how meaningful is it, but not zero is a ridiculous conclusion. So it's silly to say that simply because we're not 95% certain our result was no zero. I'm not sure, what am I getting at there? 95% certain that our result was not zero, that nothing happened. Okay, maybe we're 94% certain, P of 0.006. Does that mean nothing happened? That's ridiculous. What a stupid conclusion. It's also silly to say that simply because we're 95% certain our result was not zero, that the mean will mean something to all athletes, right? So I published that the improvement was 6%. Well, how good is 6%? Does that apply to elite athletes? Does it only apply to junior athletes? What meaning, what impact does that have on performance? So let's use the Cohen's d and the 95% confidence limits to estimate the likelihood of eliciting a meaningful change in performance. And that's really what we're after when we talk about exercise and sports science, is that we are trying to come up with a meaningful impact on performance, and we are trying to leave it in the whether to implement the intervention or not in the hands of the clinician. So my real summary, let's throw out the null hypothesis significance test because it makes us draw inaccurate, unhelpful, and potentially unethical conclusions about our results. Unethical because if we say that there was no difference, we conclude there was no difference between groups, this intervention had no effect. That's just wrong. That's an unethical conclusion. We're publishing things that are wrong. We cannot conclude there was no difference. We need to quantify the magnitude and the precision of that magnitude using confidence limits and effect sizes. Some useful background reading there as well.